If the elements are arranged in the increasing order of their atomic masses, what happens? The first element will have the properties similar to that of the eighth element. See, hydrogen actually does not belong to the first group. It is placed there separately. Why? Because in hydrogen there is only one electron which is present. So what is the general electronic configuration? I can write it as NS1. Right? For beryllium, the general one will be NS2. Right? Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So in today's session, we will be discussing on Doberene's triads, NEWLAND'S law of octaves, Mendelev's periodic table, modern periodic table, electronic configuration of elements in periodic table, S block, P block, D block and F block elements. Yes, so before moving on to what we are exactly going to study, in 1800 only 31 elements were known. By 1865 the number doubled to 63 and at present 118 elements are known and efforts to synthesize new elements are still continuing. Yes, so as of now 118 elements are known to us. See, so just imagine these 118 elements trying to study the properties, the chemical properties, the physical properties. Yes, all of the properties. How do they react with different substances? All of these properties you have to study for these 118 elements separately. How difficult a task it would be, right? So scientists, what they try to do is, they try to classify these elements into different groups or categories. Right, so that a group of elements or a category of these elements will have the same physical and chemical properties or something will be similar in them, or they will be categorized into two different categories or two different groups based on which you will be able to differentiate between each of them, right? So rather than studying all these 118 elements separately, each of this, the properties of one element is this, second element is this, right? It is a difficult task. Instead of studying it in that form, the scientists, what they try to develop a method in which they can classify elements into different groups so that the study of these elements would be easy. Right. So if we know the properties of one particular category, we can understand or get the information about the properties of all the elements which belong to that category. Right. So that was the need to classify the elements. So what is the history behind it? Suddenly one day this 118 elements were not being classified, right? And as said, in the beginning there were not 118 elements, right? It began with low numbers and then finally it has reached 118 elements. So let's try to understand the history behind it, that how these elements were classified. So in 1789, Antoine Lavoisier classified elements into metals and non-metals. So this was the first classification which was made of elements into metals and non-metals. Okay, then came into existence the Doberene's triads. So the scientist Doberene classified, how he classified elements, let us see. So Doberene's law of triads, let's see. In 1829, Doberene arranged elements with similar chemical and physical properties in groups of 3. So he classified elements into different groups which was consisting 3 elements, right? So a group of elements having, so he classified elements into a group of 3, okay? And the atomic mass of the middle element was nearly same as the average atomic masses of the first and third element, and the properties of the middle element were in between those of the other 2 members. So let's take an example and understand it. So the first group of 3 elements that he classified was lithium, sodium and potassium. So this was one Doberene's triad, okay? And then as you can see, the atomic weight of lithium is 6.9 and atomic weight of potassium is 39.1. So from this, according to Doberene's law of triads, what it is, the atomic mass of the middle element, that is the atomic mass of sodium, will be equal to the average atomic masses of the first and third element. That is, if you add 6.9 and 39.1 and divide it by 2, that is the average, right? So if you take the average of it, you will get the atomic mass of the middle element. So this was the beauty of Doberene's triads. That is, once you take the average of the atomic masses of first and third element, you will get the atomic mass of the middle element. Okay. So this was one triad. Then there was calcium, strontium and barium. That was also a group of 3. That is another triad. See, 40.1 plus 137.3 divided by 2. If you take the average of first and third element, you will get the atomic mass of the second element. Yes, and one more triad he was able to discover, that is chlorine, bromine and iodine. So 35.5 plus 126.9 divided by 2 will give you 79.9. So the same way, the average atomic masses of the first and third element will give you the atomic mass of the second element. So this is clear. So this was about Doberene's triads. Now moving on to the limitations of it. So this is not the final way in which elements were classified, right? Yes. So what were the limitations of it? It could not arrange all elements known at the time in triads. See, he was only able to formulate 3 triads, right? Lithium, sodium, potassium, calcium, strontium, barium, chlorine, bromine, iodine. These were the only 3 triads he was able to formulate. Yes, so the known elements at that time, he was not able to classify all the known elements at that time. So this was the limitation of Doberene's triads. Moving on to the second one. The second classification which was made was by Newland. It's called as Newland's law of octaves. Yes, so in the year 1865, Newland proposed his Newland's law of octaves. So let's see, when elements are arranged in the increasing order of their atomic masses, every 8th element has properties similar to that of first. So it is similar to the musical notes, right? Sa, re, ga, ma, pa, da, ni, sa. Yes, again the 8th one, that is sa, is again repeating, right? It is same as that of the first one, right? So same way, if the elements are arranged in the increasing order of their atomic masses, what happens? The first element will have the properties similar to that of the 8th element. Again, the next 8th element will have the similar properties to that of the respective first element. So as you can see here, lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. The 7 elements are the increasing order of their atomic masses. Then you can see sodium. Yes, it comes under lithium. That means, yes, the next 8th element, that is 1, 2, 3, 4, 5, 6, 7 and the 8th element will be having similar properties to that of the respective first one. Yes, the 9th will be having similar properties to the second one, right? 10th will have similar properties to third one. I hope it is clear. Yes, so then sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium. So lithium, sodium, potassium is having similar properties. Beryllium, magnesium, calcium is having similar properties. Boron and aluminium, carbon and silicon, nitrogen and phosphorus, oxygen and sulfur, fluorine and chlorine. These were having similar properties. So I hope it is clear. Yes, similar relationships exist in musical notes. So I hope you understood this. Yes, so what was the limitation of this Newland's law of octaves? So successful only up to calcium. Right, only up to calcium this classification was being able to be done. So after calcium, the elements that were discovered were not able to be included in this table. Clear? Then when noble gases were discovered, their inclusion in the table disturbed the entire table. So later on, when noble gases were discovered, they were not able to be included in this table. Yes, so according to Newland's law of octaves, after every 8th, that is, the 8th element will have similar properties to that of their respective first one, right? So when noble gases were discovered, this couldn't be happening. Yes, it disturbed the whole table. So that is what is written here. So this is what is Newland's law of octaves. Then came into existence Mendelev's periodic table. Yes, so what is Mendelev's periodic table? So before that, you need to know what is Mendelev's periodic law. Okay. So, the physical and chemical properties of the elements are periodic functions of their atomic weights. Yes, the physical and chemical properties of the elements are the periodic function of their atomic weight. So that means in Mendelev's periodic table, the elements were arranged in the increasing order of their atomic weights. Okay, he arranged elements in the increasing order of their atomic masses or atomic weights, and then there were vertical rows and horizontal rows that were discovered in this Mendelev's periodic table, and the vertical rows were called as groups and the horizontal rows were called as periods. Okay, so as you can see, this is the Mendelev's periodic table. This horizontal rows, it is called as groups, right? And the vertical rows, it is called as periods. Okay, then Mendeleev corrected the atomic masses of certain elements with the help of their expected positions and properties. So what did we understand till now? In Mendeleev's periodic table, elements are arranged in the increasing order of their atomic weights, right? So when Mendeleev was trying to develop his Mendeleev's periodic table, he was able to leave some gaps in between, wherein he was able to already predict the properties of those elements. They weren't discovered at that time, but still he was able to predict the properties of those elements and leave some gaps for them, so that when that element is discovered later, it can be added on to the table. Clear? Yes. So he left spaces for undiscovered elements and predicted its properties, right? And he left a gap under aluminium. Yes, he left a gap under aluminium and he named it as Eka aluminium, and which was being later discovered as gallium, right? And same way he left a gap under silicon, which he named as Eka silicon, and that was for germanium, which was discovered later. So this was the merit of Mendeleev's periodic table. That is, first one is he was able to arrange elements in the increasing order of their atomic weights, and he was able to predict the properties of the elements which were not discovered at that time, and he left some gaps in between so that the elements could be included later, and he was able to predict the properties beforehand itself. So Eka aluminium was discovered later, that is gallium, and Eka silicon for germanium. So as you can see in the Mendeleev's periodic table, yes, you can see certain gaps here, right? So he left certain gaps in this periodic table, Mendeleev's periodic table, so that later the elements could be included in it. And also he was able to predict the properties of the element. So yes, below aluminium, he said that a element will be discovered, that is Eka aluminium, that is gallium, right? So he left a space under that. Yes. And then Eka silicon, below silicon, some element will be discovered. Yes, he left a gap in here for gallium. Yes, I hope it is clear. So this is about Mendeleev's periodic table. Now, even Mendeleev's periodic table had its own limitation. This is not the finally accepted form of classification. So what were the limitations? It could not explain the position of hydrogen. So where exactly hydrogen should be positioned, it was not able to be explained by Mendeleev's periodic table. Then, in some cases, elements with higher atomic mass precedes the element with lower atomic mass. So, according to Mendeleev's periodic law, yes, the elements should be arranged in the increasing order of their atomic weights, right? But at certain circumstances, what happened is, all these elements were not in the increasing order of their atomic masses. There were few discrepancies there. Yes, so that is a limitation, right? So if he said that the elements are arranged in increasing order of their atomic weight, means that all the elements must be present in the increasing order, right? But there were few discrepancies in the table. Yes, the element with the lower one came in between. Yes, so that is a problem, right? And it couldn't explain the position of isotopes. So what are isotopes? Isotopes are elements having same atomic number and different mass number, right? So we have already studied what is isotopes. So he couldn't explain the position of isotopes as well. See, they are having the same atomic number and different mass number. So where exactly to position these isotopes of a single element? So that was another problem. And in some cases, elements with similar properties are placed in different groups. Right, in a group, all the elements are present in a particular group must be having same properties, right? So in this group, if I am considering this group, all the elements in this group must be having similar properties, right? So that is how the classification is done. In this group, all the elements will have similar properties. In this group, all the elements will have similar properties. But what happened is, there was a limitation that in certain circumstances, the elements present in the same group were having different properties. So that was also a limitation. So from this, the modern periodic table was formulated. So the modern periodic table was formulated by Henry Moseley. So this is the accepted form of classification. So before understanding that, modern periodic law you need to be knowing. So what it is? It is the physical and chemical properties of the elements are the periodic function of their atomic numbers. So what Henry Moseley was able to find out, that atomic weights is not the perfect way to classify elements. It is atomic numbers. So atomic numbers is the more reliable way in which the elements can be classified. So the physical and chemical properties of the elements are the periodic function of their atomic numbers. That means the elements in the modern periodic table are arranged in the increasing order of their atomic numbers, not atomic weights, in the increasing order of their atomic numbers. So we are already familiar with what is atomic number, right? So the elements are arranged in the increasing order of their atomic numbers. Elements are arranged in the increasing order of their atomic number, and there are 18 groups and 7 periods in modern periodic table. So we know what is group. It is the vertical rows which is called as groups, and there were 18 groups in modern periodic table and 7 periods. Yes, the horizontal rows are called as periods, and there were 7 periods in modern periodic table. And elements in a group are separated by definite gaps of atomic numbers 2, 8, 18, 18, 32, 32. This, what it is, I will explain it. And elements in same group have similar chemical properties. We already know that. In the same group, yes, elements will be having the same chemical and physical properties. So this is about the modern periodic table. So as you can see, the modern periodic table which is shown here. Yes, so as you can see, there are 18 groups in this periodic table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 vertical rows or 18 groups are present, right? And how many periods are there? 1, 2, 3, 4, 5, 6, 7. 7 periods, right? So 18 groups and 7 periods. And what about these two, which is represented here? This also belongs in here. So about that also I will explain now. So this is the modern periodic table. So as you can see, there are 18 groups and 7 periods. So what did we see here? Elements in a group are separated by definite gaps of atomic numbers 2, 8, 8, 18, 18, 32, 32. So what is this? Yes, so the atomic number of the first element in this group is 1 and the second element is 3. So they have a difference of 2, right? Yes, and the second element and third element, lithium and sodium. Yes, what is the difference between them? It is 8, right? Lithium is having an atomic number 3 and sodium is having an atomic number 11. So the difference is 8. Now again from sodium to potassium, the difference is 8. Then from potassium to rubidium, it is 18, right? Atomic number of rubidium, it is 37. Now again if we move from here to here, it is 18. From here to here again if we move, it is 32, right? So that is what is mentioned in this line. I hope it is clear. Now coming back to the details of the modern periodic table, right? So the first two groups that you can see, that is the group 1 and group 2, they belong to a group of elements which are called as S-block elements. So why they are called S-block elements? That is, the whole of this group 1 and 2 are called as S-block elements because the last electron fills into the S orbital. Okay, so that is why S-block elements. In detail, we will be studying about the different blocks here. So the first and second group together are called as the S-block elements, and the first element is called as alkaline metals and the second group is called as alkaline earth metals. The first group, this hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Yes, the first group is called as alkali metals. The second group is called as alkaline earth metals, and the first and second group together belongs to the S block elements. Now about hydrogen element, as you can see, the whole of it is in the same color, right? But hydrogen is different. See, hydrogen actually does not belong to the first group. It is placed there separately. Why? Because in hydrogen, there is only one electron which is present. So, hydrogen can act as an alkali metal. Also, it can act as a halogen. Yes, what is the speciality of halogen? It needs just one more electron to fulfill its octet, right? In the case of hydrogen, only one electron is present. If it gains one more electron, it can form its octet. That is called as duplet in the case of hydrogen, right? The maximum of 2 electrons can be accommodated. So, it behaves as alkali metal as well as a halogen. Yes, both are possible. So, hence it is kept in a separate box on the top. So, this is about S block elements. Now, moving on to this part, that is from group 13 to 18. That is 13, 14, 15, 16, 17, 18. All these groups together are called as P block elements. P block elements. Yes, so group 1 and 2 are S block elements. Group 13 to 18 belong to P block elements. Okay, and in this itself you can see the orange colored part is the basic metals. Yes, the orange colored part, that is the basic metals. Then boron, silicon, germanium. Yes, this green colored part is the semi-metals. And the blue colored part is the non-metals which are present. And this group 17 are the halogens, right? Fluorine, chlorine, bromine, iodine. Yes, that group is the halogens. And the last group, 18th group, is the noble gases, right? So, together all the 13 to 18 group elements are called as P block elements, in which itself you can find metals, non-metals and metalloids, right? And the last group is noble gases. So, that is about P block elements. And now coming on to the middle part. Yes, that is from group 3 to group 12. Yes, this whole blue part you can see. Yes, from group 3 to group 12, it belongs to D block elements, or it is called as D block elements. Right. Now, what about these two? Yes, as you can see here, the atomic number of lanthanum is 57. Yes, so from 57 to 71. Yes, the elements are taken out from there and they are represented here. Right. Yes, so actually they belong to this period, that is 6th period. And actinium, yes, that is present here. That is a part of the 7th period. After these many elements are present, that is from 89 to 103. The elements are actually present here, but they are separately placed here and represented here. So, these two, that is from lanthanum to lutetium and from actinium to lawrencium, this whole part is called as F block elements. F block elements. Right? So, this is S block, this is P block, and this whole blue part is D block, and the elements which were taken from here, that is represented separately, they are called as F block elements. Right? That is from 58 to 71, they are called as lanthanoids because it starts from lanthanum, right? And from 89 to 103, they are called as actinoids together, which is a part of F block elements. So, I hope this is clear. Yes. Now, the periodic table will also gives us information, like as you can see in an element, the symbol will be there. For example, let's take manganese. The symbol for manganese will be written here. The name, the full name of the element will be there. The atomic number as well as the atomic weight will be represented for each element in this periodic table. So, this is clear. Yes. Now, moving on to electronic configurations of elements and the periodic table. So, what we are going to see is from the electronic configuration, how you can say the element belongs to which period or which group. Okay, so let's see. The distribution of electrons into orbitals of an atom is called electronic configuration. You already know how to write the electronic configuration of different elements, right? So, electronic configuration in periods, let's say. So the period indicates the value of n for the valence shell. We know what is n, right? It is principal quantum number, right? So the period indicates the value of n for the valence shell. So let's take the example of carbon element. So what is the electronic configuration of carbon? Atomic number is 6. So how do I represent it? 1s2, 2s2 and 2p2. Right. So from the electronic configuration, we'll get to know the period, which period carbon belongs to. So what you have to see is the highest n value you have to see. That is, as you can see, the n value is 1 here, it is 2 here. Yes, which is the highest n value? It is 2. Yes, that means if n value is 2, that means the period is 2. Yes, carbon belongs to the second period. So from the periodic table, you can see, right, this is the first period and this is the second period. Carbon belongs to the second period, right? Yes, let's take one more example of nitrogen. Yes, the atomic number is 7, right? It is 1s2, 2s2 and 2p3. Right? Yes, the highest n value here is 2 again. So n is equal to 2 means it belongs to the period 2 or the second period. Let's take one more example of sodium. Sodium atomic number is 11, right? 1s2, 2s2, 2p6 and 3s1. Right? Yes. So highest n value here it is 1, 2 and 3 is there. So highest n value is 3. That means sodium will belong to the third period. Let us check it. Yes, as you can see here, this is first period, second period and third period. Yes, sodium belongs to the third period. So that is about the electronic configuration in periods. Now moving on to electronic configuration in groups. So let's see, elements from the same group have same number of valence electrons. Right, the number of valence electrons will be same if we move down a group. Yes, that means in this group, if I am taking the first group elements, all of this will be having the number of valence electrons as 1. Right. So in a group, all the elements will be having the same number of valence electrons. Now, how to determine the group number? Let's see. For S block elements, how do you determine it? Group number will be equal to the number of valence electrons. Yes. So let's take an example of lithium from the S block element. Right. So lithium, we know the atomic number is 3. Right. So how can you represent it? 1s2, 2s1. Right. Yes, so the group number is equal to number of valence electrons. So what is the number of valence electrons here? It is 1, right? Yes, so that is 1. That means the group to which lithium belonging is group number 1, right? So let's take another example of magnesium. Magnesium is having an atomic number 12, right? So how can I represent it? 1s2, 2s2, 2p6 and 3s2, right? Yes, so the valence shell here is 3, right? Yes, it belongs to the third shell, right? So how many valence electrons are here? It is 2, right? Valence electrons are 2 here. That means magnesium belongs to the second group. I hope it is clear. Now this is for S block elements. Right. Now coming to P block elements, how will we determine the group number? For P block elements, group number will be equal to 10 plus the number of valence electrons in valence shell. 10 plus the number of valence electrons. So let us consider carbon again, which is, of course, you know, it's a P block element, right? So carbon 1s2, 2s2 and 2p2, right? It is 10 plus the number of valence electrons. So in this case, if I ask you what is the number of valence electrons, you might say it is 2, right? So here you have to be careful. The valence shell here is 2, right? Yes, this is the first shell. This is the second shell. That is 2. Yes. So how many valence electrons are there? You have to add these 2, right? 2s and 2p, right? So there are a total of 4 electrons. 4 valence electrons plus 10 you have to do. That is 14. That means carbon belongs to the 14th group, right? Let's take one more example of nitrogen. Again, it is 1s2, 2s2 and 2p3, right? Here, what is the number of valence electrons? It is 5. 3 plus 2, 5. That means 5 plus 10 if you do, you will get 15. right? So nitrogen belongs to the 15th group. Clear? Now moving on to D block elements, how you can find it. D block elements, the group number will be equal to number of electrons in n-1 d subshell plus number of valence electrons in valence shell. So let us take an example from the D block element of manganese. Okay, manganese is having an atomic number of 25. So how do I represent it? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d5. Okay, yes, this is how I represent it. This is the electronic configuration of manganese. So as you can see, it is equal to, the group number will be equal to the number of electrons in n-1 d subshell plus number of valence electrons. So which is the valence shell here? It is 4s, right? That is the 4. That is the valence shell here. So how many valence electrons are here? There are 2 valence electrons, right? 2 plus the number of electrons in n-1 d subshell. So n value is 4. So what is n-d subshell? That is 3d, right? n-1 is 3. 3d subshell. How many electrons are there? There are 5 electrons. That means 7. So to which group does manganese belong? It belongs to group number 7. Let us check it once, right? You can see it belongs to group number 7. So I hope this part is clear from the electronic configuration of the element, how you can represent the period and group number. I hope it is clear. Yes. Now moving on to the details of each of these blocks. So first let's begin with S block elements. So as said, S block elements means the first and second group, group 1 and 2. As you can see, right? Lithium, sodium, potassium, rubidium, cesium, francium, beryllium, magnesium, calcium, strontium, barium, radium. Group 1 and 2 together are called as S block elements. So the general configuration for S block elements will be NS1 to 2. So if I am writing the electronic configuration of lithium, that will be 1s2, 2s1, right? So what is the general electronic configuration? I can write it as NS1, right? For beryllium, the general one will be NS2, right? So instead of writing it in that form, the general configuration can be written as NS1 to 2. Clear? It can be 1 or 2. Now, the group 1 is called as alkali metals, right? The group 1, lithium, sodium, that group is called as alkali metals. Group 2 is called as alkaline earth metals. So, they are generally soft metals having low melting and boiling points, and they are highly reactive and they impart colors to the flame. So, if you show the metal to flame, it starts or it catches fire and it imparts color to the flame. Okay, so there are exceptions for this, that is beryllium and magnesium. Beryllium and magnesium do not impart color to the flame. Other than that, all the S block elements will impart color to the flame other than beryllium and magnesium. And generally they form ionic compounds and they are good conductors of heat and electricity. So this is about S block elements. So moving on to P block elements, the general electronic configuration is NS2 NP1 to 6, right? Okay, and it is actually from group 13 to 18. Yes, this is 13, 14, 15, 16, 17 and 18, right? Okay, so from group 13 to 18 collectively is called as the P block elements, and it includes both metals and non-metals, right? While we were discussing about the table, yes, in the beginning, I mentioned you which parts you can see the metals, non-metals, metalloids, right? Yes. So the compounds are mostly covalent in nature. In S block elements, they form ionic compounds. Here they form covalent compounds, right? And they shows variable oxidation states. Clear? Now, S block elements and P block elements together, they are called as representative elements or main group elements or representative elements. So S and P together are called as main group elements or representative elements. Now moving on to D block elements. So the general configuration is N-1D 1 to 10, NS 0 to 2. So this is the general electronic configuration, and the D block elements consist of groups 3 to 12. Yes, 1 and 2 is S block elements, 13 to 18 is P block elements. So 3 to 2 belongs to the D block elements, and they are known as transition elements. Why D block elements are called as transition elements? Because they are in between S and P block, right? So there is a transition of properties from S to P block elements. So hence transition metals can be also called. Right. Now all are metals with high melting and boiling point. So the whole of D block is consisting of metals which are having high melting and boiling points. Now they also show variable oxidation states and form colored compounds. Yes, and often used as catalyst. Iron, cobalt, nickel, manganese, platinum. Yes, they are used in various reactions as catalyst. Clear? Now moving on to the last set, that is F block elements. Yes, so general electronic configuration is N-2 F1 to 14, N-1 D 0 to 1 NS2. So in here the last electron will occupy the F subshell. So in here the last electron will occupy the F orbital. Right. So it is also known as inner transition elements. Why they are called as inner transition elements? Yes, when we were studying about D block elements, yes, lanthanum and actinum, they are separately represented as two periods, right? They actually belong to the 6th and 7th period, but they are represented as separately as F block elements, right? So they are present inside the D block elements, right? Hence they are inner transition elements. Clear? Yes. And lanthanoids belongs from cerium to lutetium and actinoids from thorium to lawrencium. Yes. And they are all metals. Yes, D block elements and F block elements consist of all metals. And most of the elements in actinoid series are radioactive in nature. So this is the lanthanoid series starting from lanthanum, and this is the actinoid series. So I hope it is clear. So this is about S, P, D and F block elements. So what you have to understand is, in S block elements, the last electron occupies the last electron goes into the S orbital. Hence, they belong to S block elements. In P block elements, the last electron will go to the P orbital. Right. So let's take the example of carbon itself. It is 1s2, 2s2 and 2p2. Right. The last electron is going to the P orbital. Hence, it belongs to P block element. Let's take the example of lithium. It is 1s2, 2s1, right? The last electron is going to S orbital, right? Hence, it belongs to S block elements. And in D block elements, the last electron is going to the D orbital. And in F block elements, the last electron goes to the F orbital. So, I hope what and all we have discussed in this class is clear for you. So, in the next session, we will be discussing on nomenclature of elements with atomic number more than 100, metals, non-metals and metalloids, about noble gases and trends in physical properties, in which we will be studying about the trends in these three, that is atomic radius, ionic radius and ionization enthalpy, how they will change or how the trends will be along a group or along a period, how it will change, we will be studying in the next session. So I hope what and all we have discussed in this session is clear for you. That's all for today. Thank you.